We had a lot of wonderful things happening on Friday, and we have a lot of folks that we were missing. So I wanted to make sure we recorded the notes from Friday so that you guys were in good shape. So our notes up until now have consisted of understanding what the definition of momentum is and then finally getting into impulse. But now what we want to do is look at those in terms of the law of conservation of momentum. So the law of conservation of momentum is very similar in flavor to the law of conservation of energy, except instead of dealing with energy, we're dealing with momentum. So what we have are two circumstances. We have a before situation, and then we have some kind of a collision or explosion, and then we have an after. Typically what I do is I use a subscript of 1 to designate the before, and I use a subscript of 2 to designate the after. You can also use initial and final, right? You can call this the initial and final. I just had too many problems where there was a third situation that happened, so I like to number instead of using just I and F. The other piece that we have to look at is typically with a collision or explosion, there's multiple objects. So in our examples that we're going to be running through, we're just going to be dealing with 2 items. So we're going to have A and B. So this will be the term that we use to designate these. And these are our objects that are part of our collision. So we'll use the subscript 1 for initial, 2 for final, and then A and B to designate object A and object B. So what does this look like? I have my momentum initial of object A plus momentum initial of object B, and that's going to equal my momentum final of object A plus my momentum final of object B. So that's really the crux of what the law of conservation of momentum is, but let's go ahead and break that down into its parts, meaning we're going to use not just P for momentum, but we're going to break it down into the MV. So this would equal mass of A times V1 of A. Notice I'm just putting initial for my velocity because my mass isn't going to change. I'm going to add that to mass of B times V initial of B. And that's going to equal mass of A, V final of A, plus mass of B, V final of B. So this particular equation can be used for absolutely every single collision problem that we do. Today we're going to talk about perfectly inelastic collisions and explosions. And so we will have a little twist on this that makes it a little bit easier for us. But we can start with this equation every single time. So this is the gold standard for our law of conservation of momentum. Now, before we get into our inelastic collisions, perfectly inelastic collisions, we're going to look very quickly in kind of a 50,000 foot view of the 3 types of collisions that we might have. So the one that we're taking over today is going to be the perfectly inelastic. And in perfectly inelastic, we'll give a further description, but they're going to collide and stick, or they're going to be together and then blow apart. There's no combustion involved in these explosions. So don't get your hopes up. We're not going to blow anything up this chapter. Okay, so let's look at momentum. Well, when I talk about momentum with perfectly inelastic collisions, I'm looking at it being conserved. Momentum is conserved. In fact, with inelastic collisions, it is conserved. And also in elastic collisions, it is conserved. So all across the board, because it's the law of conservation of momentum, you have it being conserved across the board with every single type of collision. Now, if we're going through this chart too quickly, just remember you can pause the video or rewind and have time to write. All right, let's look about energy. And when we talk about energy, we're really talking about kinetic energy, meaning the kinetic energy before, is it equal to the kinetic energy after? So kinetic energy initial, and final. In a perfectly inelastic collision, not conserved. In an elastic collision, also not conserved. But in an elastic collision, it is conserved. Okay, it is conserved. So we'll talk a little bit more about that on Tuesday. And let's look at the last part. The last part is looking at the equation. So the equation on this one, I'm going to say C below because we're going to talk specifically about this one. I'll highlight it. We're going to see below. An inelastic collision really does not have any crazy traits to it that you would look at it and be like, oh, yeah, it's totally an inelastic collision. You kind of have to compare it with an elastic collision and find out which one it is. So we are going to use the equation above with our law of conservation of momentum. So I'm going to say C above. And so that means we're looking at this equation for that particular one. And then for an elastic collision, we are going to see above. However, because our energy is conserved, we have an additional part to that. And that's going to be KE of object 1A plus, or initial of object A, plus the kinetic energy initial of object B is going to equal the kinetic energy final of object A plus the kinetic energy final of object B. So if we want to, we can bust that out into the longer version. So that would be 1/2 ma v1a squared, which is my kinetic energy equation, plus 1/2, let me move this up a little bit, mb v1b squared is going to equal 1/2 ma v2a squared plus 1/2 mb v2b squared. Now, we will get to this again, like I said, at the beginning of next week. There is an equation that takes both our conservation of momentum and our conservation of energy and puts it together in one equation. That's kind of another little shortcut for you. So again, we'll talk about that in a little bit. All right, let's look at specifically the one that we're talking about here, which is our perfectly inelastic collisions. And we can also call it an explosion if it goes the opposite direction. So again, like we were mentioning in perfectly inelastic collision, our objects collide and stick together. Okay, so it could be, let's say 2 cars, right, come in, right? One could be going this way, one could be going this way, right? And then, of course, the collision happens, and then it's one giant mess, right, of 2 cars that have collided with each other. So it could be going head on with each other. Now, if it is that way, remember, typically when it says it's moving at a certain velocity, I automatically have it going to the right because then you have a velocity that's a positive. So moving to the right is a positive velocity. That's our standard convention. If it's moving to the left, you want to put a negative velocity on that puppy, which means that your momentum is negative. So it's possible if you have 2 equal momentums but opposite, when they come and collide, the whole thing stops and you have no momentum at the end. Because when you added the 2 things that were opposite, it gave you a value of 0. So that's possible. Well, what does the equation look like? The equation's actually kind of more simple than what we had above. So we have mass of A, V1 of A, just like previously, plus mass of B, V1B, equals. Now, in this case, because they collide and stick together, so they are connected together, their bumpers are mangled and they're connected, or it's 2 trains and they've coupled and so now they're together moving. Both masses are moving at the same rate. So I'm just going to add both of those masses and we have one single velocity because they are together. So this would be colliding and sticking together. So a lot of the equations that we're going to be using, or example problems today, we're going to be using that equation. Now, as far as explosions are concerned, that's two objects that are together, and then you have whatever your explosive event is, and let's say one of it goes one half goes one direction, and then the other part goes another direction. They could technically, if the whole object is moving in the forward direction, they both could be going the forward direction, but you never really know until you work out the math. So we're going to have a couple examples, one with a skateboard where we're not quite sure. We can kind of guess that that's what's happening, but we really want to do the math in order to be able to figure that out. Okay. So let's look at an equation for this. Our masses are together at the beginning, and they have the same initial velocity. And then at the end, they're going to break apart. So we have mass A, V2A, plus mass B, V2B. So that's the equation we're going to use for our explosions. Well, how do I know if it's an explosion or if it's a collision? The way you know is if they break apart, right? So someone's riding a surfboard, person goes one way, the skateboard or the surfboard goes another. An astronaut in space, they get untethered from their spaceship, they throw their oxygen tank away from them, and they move towards a ship. So that would be an explosion. Any two objects that are coming together, like a bullet and a block, two cars colliding, two football players colliding, all those kinds of examples would be this equation here, where you have them coming together. Okay, so let's go ahead and get into our example problems, okay? Number 1 and number 2 are very, very similar. I'm going to encourage you to pause the video and go ahead and walk through that. We aren't going to do absolutely every one of these examples. I do need to warn you that number 6 on this is actually not a perfectly inelastic collision, because it looks like the speed of the block, it emerges from the block, so they're not stuck together. So just ignore number 6. We'll cover something similar to that later on. All right, let's look at the first one. The best scenario is that we draw it out, and then we also list our variables. So we have a 13,500 kilogram, I'm going to call that object A, railroad freight car. So mass of A is equal to 13,500 kilograms. Travels on a level track at a speed of 4.5 meters per second. So it's currently my initial velocity, 4.5 meters per second. It collides and couples. So when you have a coupling of two railroad cars, it's not quite like a tow hitch, but it's kind of similar where one will kind of catch each other. So they collide and stick together. So you have a second rail car, so that's mass of B, which is 25,000 kilograms. Initially at rest, so that velocity 1 of B is going to be 0. That's the only number that you can have naked numbers. And with its brakes released, so we want to make sure there's no additional force that's preventing it from moving. Okay, so what is the speed of the two cars after the collision? Well, we want to know if the two cars are going together, then it's our final velocity that we want to know. Well, let's go ahead and draw this out. So we have one train, right? That's my train A. It's moving at 4.5 meters per second. I have train B, and it's still. And then they're going to couple. So I'm just going to put a little squiggly line there. And so then you have both trains together. And it's moving at velocity 2. And this would be mass of A plus mass of B because they're together. All right, let's go ahead and write down our equation. So we have mass of A, V1 of A, plus mass of B, V1B is equal to mass of A plus mass of B times V2. Now, first thing I look at, is there anything that I can eliminate? And the first thing I notice is I have a 0. Anytime you multiply anything by a 0, we're going to end up eliminating that entire expression. So we're left with MA V1A is equal to MA plus MB times V2. Now we want to isolate V2, which means we're going to have to divide by MA plus MB on both sides. And that will cancel out that. So essentially what we have is V2 equals massive A V1 of A over massive A plus mass of B. Now let's go ahead and put our numbers in. I highly, highly, highly encourage you, especially those of you who are going to take physics next year in the AP version, do your manipulation of the variables first. You are less likely to make a math error that way. So now we're going to plug in the numbers. So we have 13,500 kilograms. We're going to multiply that by V1A, which was 4.5 meters per second. And then we're going to add 13,500 kilograms plus 25,000. Please watch your calculator skills on this. Once you do all the math, it should come out to around 1.58 meters per second or 1.6 if you chose to not go as many decimals, okay? So that would be the answer to this particular question, all right? I'm going to have you pause the video on number 2. I will tell you that the velocity that you should have at the very, very end is 1.3 repeating meters per second. If you do not get that when you go through number 2, please make sure you see me before we move on to the next one to make sure that we are in good shape. All right, we're going to go ahead and move to the next problem. So if you haven't paused yet to check that, please do so now. Otherwise, we're moving on to number 3. Number 3 is going to be a situation where we have an explosion. So this is a little bit different. We have a 50 kilogram boy. That would be object A. And he jumps off the front of a 1.5 kilogram skateboard. So that will be object B. And he's moving forward. Okay. The boy jumps off the front of a skateboard. So initially, he's on the skateboard, right? So we have, we don't want, give me a hot minute to draw the skateboarder. Okay, that's object A. This is object B. They are together, and then it says the boy jumps off the front of the skateboard. So the boy is going to the front, going this direction, and then something is happening to the skateboard. We're not sure if it's going to the left or the right. I'm probably going to guess that it's going to go to the left, but we'll have to find out. That's going to be V2B. That's what we want to know. And this is going to be V2A. So let's look at what those values are. Find the skateboard's velocity immediately after the boy jumps, assuming that the skateboard's initial velocity, that's this whole system, so V1 is 3.5 meters per second. And the boy's velocity when jumping off the front is 5 meters per second. 5 meters per second. Okay. I'm going to guess that the skateboard is going that direction only because that's quite a speed for the child to be, or the kid to be moving off the front. And I think it's going to have the skateboard recoil backwards. All right, so let's go ahead and put that into an equation. Actually, let's go ahead and write our pieces here. So 50 kilograms for A. Mass of B is 1.5 kilograms. V1 for all of them is 3.5 meters per second. V2A is 5 meters per second. And V2B is what we want to know. So my equation would be mass of A plus mass of B times 3.0. See how easy it is to get falling into the trap of putting the numbers in. So that is times V1, and that's going to equal mass of A V1 of, or 2A plus mass of B V2b. And V2b is what we want to solve for. So in order to do that, we've got to subtract mass of A, V2A from my original equation. So mass of A plus mass of B times V1 minus mass of A, V2A. And then to get rid of the mass of B, we're going to have to divide both sides by mass of B. And that will give us V2B. If you are having difficulty with the algebra in this, please come see me. I'm happy to walk you through it. All right, so now we are at a stage where we can go ahead and fill in those numbers. So I have 50 kilograms plus 1.5 kilograms times 3.5 meters per second. And that is going to be, from that we're going to subtract 50 kilograms times V2A, which is 5 meters per second. And we're using the positive because it is in the positive direction. It says he jumped off the front of the board. So that's why I know it's in the positive direction. And then all this is going over the mass of B, which is 1.5 kilograms. All right. So when I go ahead and work all those things out, I end up getting velocity to B of negative 46.5 meters per second. So it's coming out pretty quick. That's enough to injure somebody. And it is negative, which means it's moving to the left. So the person is moving to the right. The skateboard is moving to the left. All right. So you have pretty much all the types of problems that you might see on this next assignment. We'll walk through a couple of these just to show you what we need to do in order to make the adjustment. Here we have a bullet. It's with a speed, it strikes a wooden block that's stationary. This is going to be like number 1. Cannonball with a mass of 100 kilograms flies in horizontal direction with a speed and strikes a railroad freight car with sand. That's going to be like number 1. A bullet is fired into a block. Oh, we're going to skip that one because we said it was coming outside the block, so it wasn't perfectly inelastic. And then we have a 50-kilogram boy jumps off the back of a 4-kilogram skateboard moving forward. Find the skateboard's velocity immediately after the boy jumps. This is like number 3. Okay. Let's take a look at your assignment. This is what you are going to be working on. Again, number 6, we're going to say on, because that is not a perfectly inelastic collision. Not sure how that got snuck in there. The only other thing that I wanted to draw your attention to is, for example, the football players on this question 1. They're running directly towards each other. So which one, like this is the first one that you see, and the first value of velocity is what you get. Because they're running towards each other, one of them is going to be positive, one of them is going to be negative. So just be wary of that as you're going through. The other odd one is on the back. These two are different questions, but number 8, it's not worded very well, and I promise you if this is on an assessment, it'll be worded better. This talks about a surfer jumping off the back of a 20-kilogram surfboard, moving forward, find the surfboard's velocity immediately after the girl jumps, assuming the surfboard's initial velocity is 8 meters per second. So this is an explosion, right? So you got your surfboard, and you've got your person on the surfboard. The surfboard for sure goes forward. It does not say, right, 8 meters per second is the initial velocity. And it says the girl's velocity when jumping off the board is 3 meters per second. It does not tell you if the girl is jumping forward or if the girl is jumping backward. So on the answer key, I'm going to work both of them. So you can either have her jumping this direction, which if it's moving at 8 meters per second, just to kind of give you a little bit of a reality check that's a little bit difficult to do, because she's going to have the equivalent of like 11 meters per second going backwards in order to get the reality of -3. If you want to make her travel 3 meters per second going forward, that's fine too. Just make sure you define it in your terms, like when you list your variables, And you'll get full credit as long as you let us know which one it is and you do the math correctly. If this was an assessment situation, I would tell you if it was positive or negative 3 meters per second, meaning I would tell you 3 meters per second to the left or to the right so that you could make an informed decision from there. So that one's a little bit sketchy as far as the clarity of the problem, I should say. So do whichever one you want, and I'll make sure I have both down, and we won't put you in that kind of position for an assessment. So that is your notes, and you should be good to go for the next section.